to generate our own trick. And so that process is going to look like this. I happen to have the square of 25 memorized, so in this case over here it goes plus, whoops, that's not right. Welcome to your Tuesday Math Minute, the only Math Minute guaranteed to be on Tuesday, guaranteed to be no more than 10 minutes long. We are following up the last video that we did on how to develop a math trick. And where did we leave off? What were we looking at? So we had just talked about the just above 100 trick, multiplying numbers that are just above 100, and how the area model can help us understand that trick. And I'd like to use the area model now to generate our own trick. And so that process is going to look like this. So first of all, let's pick some numbers that we want to learn how to multiply. Let's say we were going to do a trick where instead of numbers just above 100 or numbers just below 100, we chose two numbers that were just above and just below 100. So the pattern I'm thinking about is something like 103 times 97 or 99 times 101. And we want to figure out how to multiply numbers like this. Well, if you can't tell, these are numbers of the form 100 plus a, and then we're going to multiply that by 100 minus a. So each time we're going up and down the same amount from 100. 103 is 3 bigger than 100, 97 is 3 smaller. 105 is 5 bigger than 100, 95 is 5 smaller. Obviously 99 1 less than 100, and 101 1 bigger than 100. So we're going up and down the same amount from 100. We're going to take this algebraic representation, 100 plus a, 100 minus a, and we're going to put it in the box. 100 times 100, of course, is 10,000, so we always fill in that box with 10,000, or at least we have so far, as we've done a bunch of tricks centered around 100. 100 times a is plus 100a. 100 minus a is minus 100a. That's going to be useful in a moment. And then positive a times negative a is going to give us back minus a squared. Now, what we've done on other tricks is we've then written this out and tried to notice how the different terms correspond to the actual answer, to the actual product that we're interested in. In this case, you can see, oh, the positive 100a and the negative 100a actually completely cancel each other out. And so the only thing we're left with is the 10,000 and the minus a squared. So all we ever have to do to come up with the product of these numbers is think about how far away they are from 100. Again, that's what the a stands for. Square that, and then subtract that from 10,000. So going back to our examples over here, we said 103 and 97 were both 3 away from 100. 3 squared is 9. 10,000 minus 9, 9,991. 105 times 95, 5 away from 100. 5 squared is 25. 25 subtracted from 10,000 is 9,975. 99 times 101. Now, you might remember we have a different reason to already believe this is 9,999. We did something called the 101 trick a few weeks ago with two-digit numbers where we just repeat the two-digit number. But we can see now, oh, there's a different reason to think that 99 times 101 is 9,999, because both 99 and 101 are 1 away from 100. 1 squared is 1, and 10,000 minus 1 gives us 9,999. Now, you might be able to tell this particular trick is going to be relatively limited. There aren't tons of numbers that are going to work out this way, because they have to be exactly the same distance from 100. But anytime that does happen, the trick will work. And so that's how you go about developing a math trick. You could extend this if you wanted. You could say, well, what if it's not 100 that the two numbers are the same distance away from? What if it's any number that the two numbers are the same distance away from? So what if I wanted to extend the trick to something like, say, 53 times 67? So I should now be able to tell, oh, so these aren't the same distance away from 100, these are the same distance away from 60. And so is there something I could do with numbers that are the same distance away from 60? But again, I don't even want to specifically come up with a trick for 60. I want a trick for any two numbers that are the same distance, or what we call equidistant, from some other number. So let's write down a few more examples of what this might look like. 72 times 68. We might want to do 23 times 27. Those are equidistant from 25. And let's just do one more. Let's do kind of a weird one. 9 times 15. So that's equidistant from 12, but I'll say what makes that weird in a second. So what I'm going to do now is, instead of thinking about these like specifically 100 plus something and 100 minus something, obviously these are no longer centered around 100. Instead, they're centered around some unknown number. At least we don't know the number ahead of time. And so I'm going to call that A. So we're going to start from some number A. Again, in this case, A would be 60. In this case, A would be 70. A is the number that's in between the two other numbers. Here we can see A would be 25. Here we can see A would be 12. And then I need to go up and down the same amount from that number. So plus or minus B. And that's what we'll fill in next. Plus B and minus B. It goes minus 7 plus 7 plus 2 minus 2, minus 2 plus 2 minus 3 plus 3. So we would say B is 7, 2, 2, and 3. We're going to take these quantities, A plus B and A minus B, and we're going to throw them into our area model, our box method. A times A, we can no longer say, oh, that's 10, 100 times 100 is 10,000. But we can say, oh, A times A is simply the square of A. A times the B is just going to be AB. A times the negative B is going to be negative AB. And then B times the negative B minus B squared. So when we write this out, once more we notice something. The positive AB and the minus AB end up canceling each other out. And we're simply left with A squared minus B squared. This is actually a specific pattern that we call the difference of two squares. The difference of two squares always ends up describing the product of two numbers that are the same distance from some other number. So when we take that back over to the trick here, how does that help us? Well, let's think about A squared minus B squared. If A is 60, when we multiply 60 times 60, we should realize, oh, that's a 6 times 6 is 36, and then the two zeros, right? So 3,600. And then we're going to square 7. 7 squared is 49, and we're going to subtract. And so that's how we get 3,551. And that's the trick. That's what we do every time. 72 times 68. In this case, the A is 70. 70 squared is 4,900. The numbers themselves were 2 away from 70. 2 squared is 4. And so we're going to get 4,900 minus 4, which is 4,896. 23 times 27. Now, obviously, part of this trick depends on us being able to square the numbers easily. So here, A is 25, and I have to be able to square 25. Or maybe I have the square of 25 memorized. I happen to have the square of 25 memorized. I know that it's 625. And then, of course, B is 2 here. 2 squared is 4. And so this is going to be 625 minus 4 equals 621. I said 9 times 15 was a little weird because you wouldn't typically think of something involving single-digit multiplication, in this case times 9, as a process that requires a trick. And it doesn't require the trick, but the trick can certainly make it easier. Probably know 12 squared is 144. 3 squared is 9, and so 144 minus 9 gets me 135, which is the product there. I might remember, oh wait, we had a different way to multiply stuff by 9. When we were talking about the distributive property, we said 9 is the same thing, of course, as 10 times 1. And so really, when I distribute, this is going to be 10 15s minus 1 15, or 150 minus 15, which is, of course, also going to give me back 135. So one other consideration as we start to develop and make more of these math tricks for ourselves is that a lot of possible products or problems are going to have different tricks we could use to approach them. And we're going to want to get better at choosing the best trick in any given scenario. For example, this 23 times 27, I would not normally do the equidistant trick. I would normally do a different trick, which I can't get into right now, but it works like this. You take a look at the 2's, and you say, well, instead of 2 times 2, let's make one of those bigger. Let's do 2 times 3, and that's 6. And then let's just multiply the ones digits. 3 times 7 makes 21. And that's a much simpler trick than thinking through, oh wait, what was the square of 25? How far away are the numbers from 25? Square that number and then subtract. Though again, you'll notice, of course, they're going to give us the same result either way. So that is how you develop your own number tricks using the area model, using the box method for multiplication. A challenge to you for the week: can you come up with a trick for multiplying numbers just under 100 and just over 100? In other words, a 90-something times 100 and something. And I'll even give you a hint on the challenge. 90-something is best represented as 100 minus a, and 100 and something is going to be best represented as 100 plus b. So it's like the one that we developed earlier, but a and b are now different. The numbers are a different distance away from 100. Take a look at that. Be sure to give me your tricks for that in the comments down below. That is all I have for you today.